NBC states that there has been a dramatic increase in the amount of large magnitude earthquakes over the past 10 years. This seemed alarming to me. What would happen if a seismic wave destroyed your home, caused damage to your workplace or school, or even worse, hurt your family? This year, I was able to partake in a research project that combined one of my favorite topics of math, differential equations, with my concern about earthquakes. I was able to dive deep into proofs, set up mathematical models, and even talk with one of the leading engineers in the field, all while being able to answer the question, how are differential equations utilized to model viscous damping in order to ensure the increased structural stability of buildings in earthquake regions? To answer that, I had to first understand Newton's second law of motion. This equation states that the outside forces acting on the building are equal to the mass of the building times the acceleration with respect to time, plus the resistance of the building times the displacement, plus the velocity of the building multiplied by the damping coefficient. This part of Newton's second law is very important in analyzing earthquake management. If a large damping coefficient is able to be produced, the earthquake's force on the building will become insubstantial because the damping system will be able to absorb all of the energy from the seismic wave. There are many types of damping. However, the one used in earthquake management is viscous damping, which is a linear model in which the only independent variable is the instantaneous velocity of the building. This is a cross-section of a viscous damper. Essentially, the energy from a seismic wave would shake the building, causing the ring on top of the damping system to expand and compress. Inside the system, there is a fluid with a high viscosity that is able to absorb all of that energy. For my research, I was able to talk with Nathan Canny, Director of Structural Engineering at Taylor Devices, one of the world's largest manufacturers of viscous damping systems. I found out that they use a silicon mixture in their damping systems because of its longevity and the perfect amount of resistance. With my interest in math and earthquake management, I am also interested in engineering ethics. Mr. Canny and I were able to discuss at length about this, and one of the most interesting facts is that because viscous damping systems are passive and take no outside energy, they are an accessible emergency resource to all and deplete no natural resources. Thanks to mathematicians and engineers, we can all be safer during earthquakes with viscous damping systems.